Chapter 2, Section 2.2, Functions and Mappings. So we're going to begin by looking at what is a mapping and then what conditions need to be satisfied for that mapping to become a function. So a mapping, there's three elements to a mapping. You need to have two sets of numbers, so the one called an input, so very often we can do a diagram like the one over here. An input here will be the set A, and you can have the output. The third element is a rule that links the input to the output, so some way of connecting the elements of set A with elements of set B. So this is a mapping, so you transform sets from A onto elements in set B. Okay, so for for a mapping to exist, another rule is that every element of A must have an image in B. So here, all of these examples that I've drawn are examples of mappings. So these examples here represents each set A as the input and each set B as the output. In the first example here, you've got every element of A has a unique output, and that output is in set B. This type of mapping we are going to call 1 to 1. The second example, you've got two elements of A. You could have even more than two, but they are being taken to, well, some of them are taken to one element in B, and so each element in A has an image in B, but it's not necessarily a unique image. This is called many to one. So for example, this could be squaring. So we could do squaring, and the elements could be -1 and 1. The image of these two numbers is 1. -2, 2. The image of these two numbers is 4. But if I have 0, if I square it, it will just go to 0. So this is an example of many to one mapping. And this one here is one to many, because you could, at least if there's at least one element in A that has two different images, then it will be called one to many. Now, what makes these mappings function? So as long as the following rule is obeyed, so no element of A must have more than one image. So as long as we are not allowing one to many, then it will be a function. So a function, if it is a 1 to 1 or many to one mapping, then it's a function. Okay, each set of input elements is called the domain, and the set of outputs is called the range, which you should know from last year. So if you consider the following function, well, it's not a function. If I just state here it is, that would be a mapping. So if you draw it, it will look like half of a parabola on its side. Now, you cannot call it a function because we do not know the clear inputs, the domain. So the domain must be clearly defined. So the domain for this function to exist, and the domain is anything belonging to real values, so all the x's belonging to real values, such that x is greater or equal to 0. So this is the domain. Once we've done that, because we cannot square root negative numbers, we know that every element of the domain will have a unique output. So this is also going to be 1 to 1 function. As you can see that for every element on the positive x-axis, you will get an output, and it will be unique for that particular value. We're going to have a look at example 7. So in the example 7, the question relates to 4 different graphs. We are asked to state if those mappings, diagrams that are shown as mappings, the diagrams of the mappings are 1 to 1, many to 1, or 1 to many. So in example A, you could see that there is one element here that is taking me to 2 different outputs. So if there is at least one situation like this, then you can call it 1 to many. So is this a function? No, because you are not allowing more than one image if it's a function. The second one here, you can see it's a graph of a straight line, y equals 2x plus 5, and every possible values of x on the x-axis will have a unique output. So you are hitting the line at a single point for every different position of x, which will take you to a different height, so different value of y. So this is 1 to 1. And it's definitely a function if we clearly state that x belongs to real values. So this is the domain. C, this is the graph of y equals 1 over x. Now, if you could see that for this number, if I take it up to the curve, go across, it will find the value over here. If I go to this number, you will have a value, another value. So you will get a unique answer for each unique input. You'll get a unique output. So it's 1 to 1 mapping. Now, however, this is not going to be a function until we describe the domain correctly. So not a function unless we say that x's are real values apart from this value when you are going to be on the y-axis, which is for x equals 0, because then it's an asymptote. So the asymptote is x equals 0. The last example, it's a quadratic function, y equals x squared minus 1. I'm calling it a function straight away without even considering whether it is a function or not. So let me just first of all say whether it's 1 to 1 or many to 1 or 1 to many. So you can see that there's 2 possible values of x here, one x and one opposite in value of x. It will take me to the same value of y. So this is called many to 1. So if you can find just one example of that, then it's what it's called. If we're talking about whether it's a function or not, it is going to be a function if we clearly state the domain. So x belonging to real values, you can see there that all possible values of x can be substituted into this function to obtain the y values. Okay, so let's move on to example 8. In the example 8, again, you've got 3 questions, and in those 3 questions, you've been asked to find the range and then state whether it's 1 to 1 or many to 1. That's right. So in this particular example, the domain is only the set of 1, 2, 3, 4 numbers, and they happen to be 1, 2, 3, 4. So to find the range, we are going to substitute the values of x into the f of x. So it's 1, 2, 3, 4. And let's put it into, so times it by 3 and minus 2. So you're going to get 3 times 1, which is 3 minus 2, gives you 1. 2 times 3, which is 6, take away 2, which is 4. 3 times 3, which is 9, take away 2 is 7. 4 times 3, which is 12, take away 2 is 10. And these are my y values. So the range is going to be y belonging to real values, and y is equal to 1, 4, 7, 10. I don't need to put the y belongs to real values. There's only 4 of those numbers. Okay, so is it a one-to-one or many-to-one? And you can see that each input has its own distinct output. So this is going to be 1-to-1. Okay, doing the same to those numbers, you've got x squared. This is a continuous set of values, so we're going to sketch it. So if you think about the quadratic function y equals x squared, it looks like this. And we're going to find the end values, 5 and minus 5, see what they take me to. So g of minus 5 is equal to minus 5 squared, which is 25. And in fact, the positive will also take you to that value, 25. The end parts of the curve belong to the function. So what are the possible values of y or g of x? Well, you have the lowest value at 0, and the graph definitely passes through that, so you'll be getting that value. And the high value is 25. Again, you get this value because the end values were included. So the range, you will have y belongs to real values, and then y starts from 0, goes all the way to 25, or g of x rather than y. Now, for those two values of endpoints, for 5 and minus 5, it takes you to one answer. So this is an example of many to 1. Okay, part C, you've got a reciprocal graph, 1 over x. So for any quadratic and reciprocal graphs, I will always sketch this graph. So if we sketch 1 over x, 1 over x looks like this. There are 2 branches. However, we are only interested in the part from 0 up to 3. Now 0 takes you from the asymptote, so from that point. When it's 3, let's work out what age of 3 is. This is 1/3. So that will take you to that point, and it's definitely belonging to that value. So the graph in question is only that part, top part of the right branch. So you don't have those parts at all. So looking at the y-axis, what are the possible y values? Anything from 1/3 all the way to the infinity. So the range will take you from y equal to 1/3 and upwards. For any value on the x-axis, you will get a unique y value anywhere you go from 0 to 3. There you go. So this is a 1-to-1 function. So 1-to-1 function, if you can just imagine straightening it to make a line, that will always be a 1-to-1 function. If it's more like squiggly, like a parabola, so it comes back onto itself, or it's a sine graph, then it's going to be many-to-1. If it's anything like a circle, then it's not going to be a function, because it will be 1-to-many, which is not allowed. Okay, so one more example before exercise 2b. So in this case, you've got a function f of x defined as by two different parts. Okay, so this is called a piecewise function, so where you have part of it as a straight line and part of it as a quadratic function. So first thing is we are asked to sketch this function. So if we sketch it, you've got a straight line y equals 5 minus 2x. Our line actually should start from x equals 1. So x equals 1 is somewhere here. So for x is less than 1, I do apologize, not greater than 1. So it's from 1. So we're talking about that part of the straight line. Not very tidy, but that will do. And then for the quadratic function, it's for x greater and equal to 1. So we're starting from this position here. So this actually hits you at the point that will be at 4. This is 0, this is 1, 4. And then you've got this part of the quadratic function. There you go. So you have the full parabola. So on the left hand side we've got a straight line, and then on the right hand side we've got a parabola. Now state the range. So the range of this function is, you could just imagine going up the y-axis. Your first value you're going to obtain is when you hit this value here. So that was when x was equal to 1, and it took you, if you work out what it is, it's 5 minus 2 times 1. That will take you up to 3. So this point is 1, 3, and then you get all the values above it. Now 1 is not, the 3 will not be included. So the range y is greater than 3. You could write it y belongs to real values and y is greater than 3 in the set notation. Now you're asked to solve this equation f of x equals 19. So it's not going to be to scale, but if you imagine y equals 19 somewhere at the top part of the y-axis, we're talking about two possible solutions. We're going to find these two solutions. So we've got to solve two equations. We're going to make 5 minus 2x equal to 19, and that will give us 2x is equal to 2 minus 19, which is negative 17. X is equal to minus 8.5. And the second solution, x squared plus 3 is equal to 19, and that gives me x squared is equal to 19, take away 3 is going to be 16. So two solutions, plus or minus 4. Right, let's look at the diagram. If you look at the intersection with a straight line over here, this point A, that will correspond to minus 8.5. So this goes with point minus 8.5, 19, but the solution is x equals minus 8.5. Now the second solution that you'll find, you'll get it by finding the intersections with the parabola. There's two of them, one at x equals minus 4, one with x equals plus 4. So if you look at the diagram, point B is going to be the positive solution, so it's going to be 4 and 19. So x is equal to 4 is the required solution. Just make slight correction here. That was 5 here, copied that incorrectly. It's 5 minus 19. So 5 minus 19 should be minus 14, taking us to minus 7. So x is equal to minus 7 is the first solution. X is equal to 4 is the second solution.